My name is Kai, currently a PhD student at KAUST. My supervisor at Vector Institute is Professor Yaoliang Yu. Today, I would like to share our recent project, efficient variance-reduced methods for stochastic bilevel optimization. For this presentation, it seems it's a bit different from the previous presentations because this one is more theoretical. So I will give more background as much as possible. Firstly, let me start from the single level finite sum optimization. We are going to minimize phi x, which is defined as the finite sum of fj's. M is the number of nodes or the number of machines. D is the dimension of the global model parameters. And Fj is what we call the local objective. The difference of our focus, stochastic bilevel optimization, SBO, and the single level optimization problem is the construction of the local objective Fj in SBO. Fj is not only depending on x, but also the optimal y given x. Y star is being optimized as the argument of the finite sum of gix given y and x. For any gradient-based methods, we need to compute the gradients for the learning rule. So here, for the stochastic bilevel optimization problem, we need to compute the hypergradients. Under proper hypothesis and using the implicit function theorem, we can show the gradients phi x as follows. Apart from the standards x and y, here involves in another variable v. The optimal v star given x is the solution of the linear system mentioned below. Why we start the stochastic bilevel optimization problem? This is popular in hyperparameter tuning and mental learning. Let me give you the example of hyperparameter tuning. So suppose this phi x is the training objective. After training, we get a good x. Then we use this model x. We are going to work on the validation set, which is the finite gi. Then we want to do good on this finite gi as well. So here, the outer problem, Fj is the training step. The inner problem, gi is the validation step. This is the example of the hyperparameter tuning for SBO. So what's the difficulty of stochastic bilevel optimization? At least from our perspective, there are three essential challenges. Firstly, as we can see from the structure of SBO, an intuitive way is to first obtain a good estimation of the optimal y star or just compute the exact y star given x. And then use this y star given x, we optimize the phi x. However, these two loop methods is always not efficient, and it requires additional computations. On the contrary, the single loop methods involves in the computation of the x and the y at the same time. However, we found in theory it's always very hard to prove this kind of method. The second challenge is involving in the computation of the hypergradients. As we can see from the previous representation, This hypergradient involves in the Hessian inverse, which cannot be computable for some real scenarios. And also, it involves in numerous second-order computations, which is very costly. The last challenge involves in the stochastic estimation in SBO. It will result in high variance during the training step. However, designing an efficient variance-reduced methods is very, very difficult. Since the two-loop methods cannot solve SBO efficiently, we should have we need to focus on the single loop methods. So here we consider this fully single loop representation and proposed our method SBO-LSVRG. The brief idea is that we optimize Y, V, and X at the same time according to their unbiased direction, dyt, dvt, and dxt. So like mentioned, those are unbiased estimator of the real gradients dy, yvx, dv, dx as well. The explicit form are presented at the right-hand side. So I don't know why it runs automatically. So for this, we list the variance-reduced methods for solving SBO. Before our work, the state-of-the-art method is SABA. It achieved the optimal complexity. However, to reduce the variance involved, it needs to have extra space to store external variables. However, our proposed method SBO-LSVRG achieved the optimal iteration complexity, but without introducing too much additional variables. Our space complexity is aligned with other baselines such as SVRB and VRBO. So the main intuition comes from the difference between loopless SVRG and SAGA, because SABA is based on SAGA, while our method is based on the loopless SVRG. Suppose now we are going to sample index I uniformly at random. For SAGA, it involves in the computation of n local auxiliary vectors. However, for loopless SVRG, we only need to store one global auxiliary vector, which is space efficient. And then we have the update rule of this SBO-LSVRG. It involves in 6 different variables for the inner problem G and the outer problem F. The explicit form of this update rule is presented as follows. We can see the sketch of the loopless SVRG behind, but actually the proof can be far more challenging than the previous work. And under standard assumptions, we can show our proposed SBO loopless SVRG has the following convergence rates. So the convergence rate is m times n 2/3/t, which is optimal. And we provide additional analysis for the single level case and then the other variance. So if we assume the learning rates of rho to be always 0, then we will obtain the rates n 2/3 epsilon minus 1 for the single level optimization problem, which is optimal. Also, we are the first to present the convergence rates of loopless SVRG type methods under the non-convex setting. And if we consider the special case by letting m equals to n and let gi to be equal to fg, then we will get exactly the minimax optimization. For those who are very familiar with generative adversarial network, you will find gains are exactly under the minimax optimization scope. And we achieve the iteration complexity to be n2/3 epsilon minus 1, which is also the optimal for minimax optimization. Here are some useful reference for this presentation. Here are all what I would like to present today. Any questions? Sorry for that. There is some problem with my slides. It will always play automatically. So I don't know what to do with that, but I hope it doesn't affect too much.
No, everything looked great from here. So we'll just take a couple questions for you.
Mm-hmm.
Hi, thanks for the presentation. Did you note any, or did you find any optimization failure modes or failure cases that were maybe interesting in this case when you're doing experiments?
So if I understand correctly, you mean what the real scenario we can consider in practice, right? So basically,
yeah, kind of like if you noticed any maybe failure cases or anything like that, and maybe if there are links with any other strange behaviors, I guess.
Yeah. So basically, there are two different perspectives. One is just like I mentioned here, the stochastic bilevel optimization is more general than the standard finite-sum optimization task, which is widely used in practice. And another thing is the minimax optimization is also a special case of the general stochastic bilevel optimization. That means any analysis on top of generative adversarial networks can be safely applied during the within the scope of our analysis. Another perspective is that for solving stochastic bilevel optimization, it involves in some specific characteristics. Like I mentioned, the mental learning can be aligned within this framework, and the hyperparameter tuning, or even the automatic weight selection, or even some other extensions can also be included in this framework. Indeed, this is a theoretical heavy work, but we are happy to extend this and include some experiments to validate efficiency in practice.